Block 1. Physics Time Problem. At the very heart of modern physics, there's a chasm, a deep and unsettling crack in our understanding of reality. On one side stands our greatest theory of the cosmos, Albert Einstein's general relativity. It's a theory of the monumental, describing gravity, galaxies, and the grand sweeping architecture of the universe. In this picture, time is not a rigid, universal metronome. It's a character in the story. It's woven into the very fabric of existence, a dimension that can be stretched, squeezed, and warped by the presence of matter and energy. We call this four-dimensional tapestry space-time, and in Einstein's world, your experience of time depends entirely on where you are and how you're moving. Time slows down near a black hole. It ticks infinitesimally faster on a mountaintop than it does at sea level. This isn't science fiction. The GPS in your phone has to correct for this relativistic time dilation every single second just to function. For Einstein, time is dynamic, local, and relative. It's a flexible river, not a rigid ruler. But on the other side of this chasm is our other masterpiece, quantum mechanics. This is our theory of the minuscule, the world of particles, probabilities, and spooky interactions. And in the standard formulation of quantum mechanics, time is something completely different. It's an outsider. It's a background parameter, an absolute, unchanging stage on which the quantum drama unfolds. A rigid, ticking clock that dictates the pace of change for everything, everywhere, all at once. The famous Schrödinger equation, which governs how quantum systems evolve, has a special place for t, time. It's the independent variable that drives all the change, the universal metronome that quantum mechanics relies upon to make sense. Here lies the paradox, the fundamental conflict that has kept physicists awake at night for decades. We have two spectacularly successful theories that form the bedrock of our understanding, yet they are built on completely contradictory notions of time. One sees it as a flexible, internal part of the universe's geometry, while the other treats it as a rigid, external background. This isn't just a philosophical disagreement, it's a mathematical roadblock. This conflict becomes a crisis when we try to describe things that are both incredibly massive and incredibly small, like the singularity at the heart of a black hole or the very first moment of the universe at the Big Bang. To understand these ultimate frontiers, we need a theory that can bridge the gap. We need a theory of quantum gravity. In the 1960s, two brilliant physicists, John Wheeler and DeWitt, embarked on one of the most audacious projects in scientific history. They decided to try and write down an equation that would do just that. They wanted to apply the rules of quantum mechanics not just to an electron or a photon, but to the entire universe itself. Their goal was to find the quantum recipe for reality, to create a wave function for the universe. In quantum mechanics, a wave function describes all the possible states a system can be in, where a particle could be, what its momentum might be. So a wave function for the universe would, in principle, contain all the information about every possible state of our entire cosmos. It would be the ultimate master equation. They started with Einstein's equations for general relativity, which describe the geometry of spacetime. Then they applied the standard procedure of quantization, the same set of rules that turns a classical description of a particle into a quantum one. It was a fiendishly difficult mathematical task, pushing the limits of theoretical physics. But when the dust settled, they were left with a single, elegant, and utterly terrifying equation. This was the Wheeler-DeWitt Equation. It looked like a version of the Schrödinger equation, but for the entire universe. It had a term representing the geometry of space and a term representing the matter and energy within it. But there was one thing stunningly, shockingly absent. The t was gone. The variable for time, the very thing that drives all change in the normal quantum world, had vanished completely from the mathematics. The t for time simply disappears from the final equation. Why did it disappear? In essence, when you quantize the entire universe, you run into a unique problem. The universe contains everything, including all the clocks and all the rulers. There is nothing of the universe to measure it against. In general relativity, time is defined by the changing geometry of space-time itself. But if you are describing the quantum state of that, there's no external clock left to observe its evolution. The universe becomes its own clock, and in doing so, the concept of an overarching external time becomes meaningless. The equation simply says that the total energy of this timeless universe is zero, and that's it. The wave function of the universe, psi, doesn't depend on time. It just is. This leads to the most profound and disturbing implication in all of science. If the state of the universe doesn't change with time, then on a fundamental level, nothing ever happens. The universe, according to this master equation, is frozen. It's a static, timeless sculpture. This is what physicists call the problem of time, and it suggests that our entire perception of a flowing, changing reality might be a grand illusion. Frozen universe implications. So, we're left with this staggering paradox. The Wheeler-DeWitt Equation, our best attempt at a fundamental description of reality, paints a picture of a static, timeless universe, a frozen block. Yet, you and I experience something completely different. We experience birth, growth, and decay. We remember the past, live in the present, and anticipate the future. We feel the undeniable, relentless passage of time. How can we possibly reconcile the frozen universe of the equation with the dynamic, flowing universe of our experience? This question has fractured the world of theoretical physics, leading to some of the most mind-bending interpretations of reality ever conceived. One radical interpretation takes the equation at its word. This is often called the block universe view. It suggests that our intuition is simply wrong. In this model, all of time, every single moment from the Big Bang to the heat death of the cosmos, exists simultaneously, eternally, and on equal footing. Reality is a cosmic movie reel where all the frames exist at once. The past isn't gone, and the future isn't unwritten. They are all just different coordinates in the four-dimensional block of spacetime. Our consciousness in this view acts like a spotlight moving along this pre-existing reel, illuminating one frame at a time, creating the powerful illusion of flow and passage. The feeling that the present is special is just a feature of our perception, not a feature of reality itself. The philosophical implications of this are immense. If the future already exists in the same way the past does, what does that mean for free will? Are our choices merely the discovery of a path that was already laid out in this timeless block? It's a deterministic view of the universe that many find deeply unsettling, suggesting our lives are not stories being written, but a book that is already finished, which we are simply reading line by line. However, most physicists lean towards a different, and perhaps even more profound idea. Time is not fundamental, but it's a secondary, macroscopic phenomenon that arises from a more fundamental, timeless reality, much like other properties we see in the world. Consider temperature. A single water molecule doesn't have a temperature. Temperature is a meaningless concept for one particle. But get trillions of them together, and their collective random motion gives rise to the property we call temperature. Temperature emerging from the motion of molecules. Temperature isn't fundamental, that emerges from the statistics of a complex system. In the same way, time might emerge from the quantum relationships between different parts of the universe. A groundbreaking idea known as the Page-Wouters mechanism suggests that quantum entanglement is the key. Entanglement is the spooky connection where two or more particles become linked, sharing a single quantum state. The idea is that while the universe as a whole is static and timeless, you can split it into two parts, a clock and a system. An observer inside the universe would see the system evolving relative to the clock due to the entanglement between them. For this internal observer, time would appear to flow perfectly normally. It's only from a hypothetical, godlike perspective outside the entire universe that everything would appear frozen. We are not outside observers, we are subsystems of the universe. Therefore, the time we experience is the result of tracking the correlations and entanglements between our part of the universe and the rest of it, which acts as our clock. Time, in this view, is a relationship, not a substance. This idea of emergent time also helps explain the arrow of time, the fact that we only experience it moving forward. This is deeply connected to the second law of thermodynamics, which states that the total entropy, or disorder, of a closed system always increases. The universe began in an incredibly low entropy, highly ordered state at the Big Bang. The reason we experience time flowing in one direction is because that is the direction of increasing entropy. An arrow of increasing entropy. You can unscramble an egg in principle, but it's astronomically improbable. We form memories of the past because they are records of lower entropy states. We don't remember the future because it is, by definition, a state of higher disorder that hasn't happened relative to us yet. The arrow of time we perceive is not a fundamental law, but a statistical likelihood rooted in the unique starting conditions of our cosmos. Of course, the Wheeler-DeWitt Equation is not the final word. It's plagued with its own severe mathematical difficulties and is more of a conceptual framework than a fully predictive theory. Competing theories of quantum gravity, like string theory and loop quantum gravity, offer their own unique perspectives. Some versions of string theory require extra dimensions and a background spacetime, potentially preserving a more conventional role for time. Loop quantum gravity, on the other hand, suggests that spacetime itself is quantized into discrete atoms of space and time, which might mean that time flows in tiny, indivisible ticks rather than as a smooth continuum. The debate is far from over. This is the bleeding edge of science, where physics dissolves into philosophy and mathematics becomes a tool for exploring the very nature of being. We are left standing at a profound fork in the road. Either our deepest physical equation is fundamentally flawed, or our most basic, intimate experience of reality, the steady, flowing river of time, is nothing more than a stubborn, persistent, and beautiful illusion emerging from a silent, frozen, and timeless ocean of existence.